Ever pondered over the perplexing world of quantum mechanics? Welcome to the realm where the usual rules of physics take a back seat and the unimaginable takes center stage. Consider this: tiny particles called photons that can be in two or more places at the same time. Yes, it's as if you're in your living room and at the grocery store simultaneously. This is what we call superposition in quantum mechanics. Now let's add another layer of complexity. These photons, when measured, suddenly choose one state. It's like flipping a coin that's spinning midair, and it only decides whether it's heads or tails when it hits the ground. And the most intriguing part? Until that measurement, the photon exists in all its possible states simultaneously. Quite mind-boggling, isn't it? But hold on, it gets even more fascinating. Welcome to the world of quantum mechanics, where the impossible becomes possible. Imagine wanting to share a secret message with someone. How would you ensure it stays secret? Here's where the magic of quantum encryption steps in. Quantum encryption is like the superhero of the digital world, safeguarding your secrets with powers derived from quantum mechanics. At the heart of this superpower are quantum bits, or as we call them, qubits. Unlike regular bits in classical computing, which are either a 0 or a 1, qubits can be both at the same time. This ability, called superposition, allows qubits to carry more information than classical bits, making them the perfect tool for creating unbreakable encryption keys. So when Alice wants to send her secret message to Bob, they use these qubits to create a unique key, a secret code, if you will. This code is so secure that even if someone tries to eavesdrop, the code changes, thanks to another quantum phenomenon known as entanglement. And that, my friends, is how quantum mechanics can protect your digital secrets. Ready for some eerily fascinating stuff? Let's dive into the enigma of quantum entanglement. Picture two particles that are inextricably linked, like cosmic dance partners. Even when they're galaxies apart, they remain connected. Change the state of one, and the other responds instantaneously as if they are one. This isn't just a science fiction tale, it's a fundamental principle of quantum mechanics. Now, you might be wondering, what does this have to do with cryptography? Well, this spooky action at a distance is the backbone of quantum cryptography. This instantaneous connection allows for the exchange of information securely, even over vast distances. Imagine being able to send a message from Earth to Mars with the assurance that no one else can intercept it. That's the power of quantum entanglement in cryptography. Quantum entanglement. Spooky, isn't it? But it's what makes quantum cryptography so robust. Ever seen particles perform a dance? We're about to dive into the fascinating world of quantum key distribution, or QKD, a dance of particles that's as complex as it is intriguing. Imagine this. Alice and Bob, our daring duo from earlier, are ready to exchange secret keys. But they've got to do it without anyone intercepting their dance. In comes QKD, their dance floor, where they can prance around, exchanging quantum-encoded keys with confidence. Here's how it works. Alice begins by preparing a series of photons, particles of light in random states. She then sends these photons to Bob over a quantum channel. Bob, on his end, measures these photons using a random set of filters. He records the results but doesn't share them just yet. Following this, Alice and Bob publicly compare their random choices, but not their actual measurements. This is crucial because it allows them to discard the bits where their choices didn't match. The remaining matching bits form their secret key. But what if an eavesdropper, let's call her Eve, tries to intercept their dance? Here's the beauty of QKD. If Eve tries to measure the photons, she'll disturb their states due to the Heisenberg uncertainty principle. This disturbance can be detected by Alice and Bob, alerting them to Eve's sneaky presence. And that's the quantum key distribution dance, a choreography of particles, if you will. But it's all theoretical, right? Wrong. Quantum cryptography is not just a fascinating theory, but a practical tool that's already making ripples in our digital world. Let's dive into some real-world applications. Sensitive government communications, for instance, are one area where quantum cryptography is playing a critical role. In a world where information is power, ensuring the secrecy of governmental affairs is paramount. Quantum cryptography helps protect these vital communications, making it nearly impossible for any third party to eavesdrop without detection. Now, shift your focus to financial transactions. Every day, billions of transactions happen around the globe. From transferring funds to online shopping, our financial activities are ripe targets for cybercriminals. But don't worry, quantum cryptography is here to the rescue. By employing quantum encryption, these transactions can be secured, keeping our hard-earned money safe from prying eyes. But that's not all. The potential of quantum cryptography stretches far beyond these examples. It's set to revolutionize cybersecurity as we know it. As we inch closer to a world where quantum computers may crack traditional encryption methods, quantum cryptography emerges as our knight in shining armor, ready to protect our digital world. So, when you think of quantum cryptography, don't just picture a theoretical concept. Envision an active player in our daily digital lives, a bulwark against potential cyber threats. Quantum cryptography, it's not just a concept, it's already here, protecting our digital world.